everyone. Good afternoon. I am Nanda Mitra Pammi from IIIT Bangalore, India. Today, I am going to be presenting our work on FlexGlove, grass-based 3D object reconstruction using wearable sensors. The paper ID for this session is 5694. The co-authors to this paper along with me are Mr. Mohit Jagini and Mr. Madhav. I sincerely thank the IEEE Census 2025 Selection Committee accepting this paper. I also thank the IEEE Census 2025 Committee for providing me this opportunity to present this work with you all. So let me get started. Abstract. So what are we doing? We have developed a 3D object reconstruction based glove using flex sensors. There is a flex sensor glove which has 5 flex sensors, one for each finger of the hand. Segment-based modeling and dataset creation. What do I mean by that? I mean to say that the segment-based modeling it is repeated grasps. So the entire reconstruction is based out of repeated grasps of the object. This was made by us, and the dataset further was made by us completely. The grasps have been predefined. It has been evaluated on 6 people on both of their hands, and the real-time visualization module of Blender, CAD module basically runs in the background, reconstructing the object. So, why do we need this? We were searching for a reconstruction-based method, and we found that most of them are reliant on camera-based methods, or the ones that are not are heavily dependent on mathematics, complex sensors, substantial computing power, and intricate calibration processes. For low cost, scalable, and real time applications, these weren't really feasible. So we thought of a module which would be feasible for low cost for everyday objects in particular. It should be economical, is the main point. And hence, we came up with a flex sensor glove using a Raspberry Pi model of 3B microcontroller. This, I would like to clarify that we are taking an assumption that the shapes are smooth and we cannot uh, classify any irregularities that we find on the shapes. The use of low-cost flex sensors to capture finger positioning contributes to the overall affordability and low cost and accessibility of the system. A simultaneous CAD program is running in Blender in the background, reconstructing the object in real time. So system over. So the glove classifies cylinders, cuboids, and spheres based on distinct grip patterns and predicts their dimensions through multiple grasps covering the entire surface. So why cylinders, cuboids, and spheres particularly? It is because we have noticed that everyday objects are mostly cylinders, cuboids, and spheres. And hence we decided that they should be our main target objects with respect to classification and determining their dimensions. So for each of the shapes, we decided a fixed gripping pattern. So to calculate the radius of cylinders and spheres, the glove assumes a typical grip pattern where anyone would normally hold how they would hold a ball or a bottle, as in a ball with their hand, however, and the bottle and ball representing spheres and cylinders. So now the next problem is getting the height of the cylinder. The fist size is usually about 7 centimeters, the size being the height. So hence, we decided that every cylinder could be split into multiple smaller cylinders, and each of them would have the height of 7 centimeters, and they would be reconstructed in real time by stacking one over the other. This would also help us if there were cylinders of different radius stacked over one another. So, Now, once the user of the glove keeps gripping it on and on until he reaches the point where the height of the cylinder left is less than 7 centimeters, the user or the glove has been designed in such a way that the person has to straighten out the fingers which are not in contact with with the cylinder. This would give the correct approximation of the height of the cylinder. As we can see in this circuit diagram, there's a Raspberry Pi 3B microcontroller, an MCP3008 ADC converter, and 5 flex sensors. We are using the ADC because the values from the flex sensors are in analog form and the Raspberry Pi needs it in digital form. So we have used an ADC converter. The interface used is the SPI interface. So for cuboid, the cuboid gripping pattern has been determined with respect to the size of flex sensor. The size of the flex sensor is approximately 5.6 centimeters. And hence, we decided that the person is to keep his hand straight on the cuboid and keep moving it by 5.6 centimeters every 5 seconds until he reaches the point where the length left is less than 5.6 centimeters and then he grips it completely, he or she. So this is done for all the dimensions for a full 3D reconstruction. So how does the system work? We get an input from a flex sensor glove. These inputs are analog values which are converted to digital values using MCP3008 mode. Now, we read the digital values using SPI interface on Raspberry Pi 3B. Next, a classifier module runs in the Raspberry Pi. This classifier module and regressor module have been made available in a GitHub repository given at the end. The classifier decides whether it is a sphere, cuboid, or a cylinder. Once the classifier does the decision, a regressor gets into action and decides the dimensions of the shape. And then it next goes to the CAD output, which is running in the background, reconstructing the shape. So the data set was collected manually as said earlier. So we had taken approximately 23,000 samples for this classification. 8,000 samples were cuboid and cylinder, and around 7,000 were sphere. So spheres was not. So how have we collected it? What is the gripping pattern? The gripping pattern has been discussed earlier. Now, the main differentiating pattern between all the classes is the gripping pattern itself. The cuboid gripping pattern was taken in such a way that there cannot be conflicts with other shapes, as in it's always a straight grip or you bend it. And hence we found that cuboid classification shows excellent results. So our main problem was with cylinder and sphere, since they are both almost wrapping around the object. And hence, for the radius particularly, we found that they are comparing, and hence we took a lot of uh, data for this. So around zero point 0.5 centimeters, 1 centimeter, and so on till 8 centimeters for the sphere radius. And for the cylinder radius, also similar to that, zero point 0.5 centimeters to 8 centimeters. We had taken objects of those sizes and created a data set for prediction of radius. And hence, for the cylinder, there is also a thing of height. And hence, we had created a data set further where one finger is straightened out, two fingers are straightened out, three fingers are straightened out for different radius, as discussed before. All of this was useful in classification and then regression. So, a random forest module was used for this. Random forest classifier using 100 estimators identifies the object shape and then separate regressors estimate the dimensions of the shape. This model performs accurately well within the trained ranges as said before, but shows reduced reliability when extrapolating past that 8 centimeters of radius as discussed earlier. So we are working on that. Results. The mean absolute error for reconstructed cuboids, cylinders, and spheres was observed to be 0.33 centimeters, 0.23 centimeters, and 0.01 centimeters. You can further see a reconstructed book and a bottle below. I would now like to share a video where we have shown how the reconstruction works for different shapes. So for a book, the length is 29 centimeters. The breadth is 20.5 centimeters. The height was about zero point 0.8 centimeters. And we can see the gripping pattern here in the video. I would like to further point out that this video has been made available at the end of the PPT. So the width is 0.9 centimeters, and we can see the rest. Predicted radius is 3.57 centimeters when original is 3.5 centimeters. Report. Radius is about 3 centimeters. Height is about 21 centimeters. First subpart, as I said, when we stack a cylinder on top of each other. So 3.16, 3.15, 3.03, and height, it comes out to be 2.1, 21 centimeters. Now, I'd like to get back to my presentation. And hence, as seen in the video, the mean absolute error is indeed about 0.33 centimeters for cuboids. For cylinders, it is 0.23 centimeters. And for spheres, it is 0.01 centimeters. The classification reports are given. The precision recall and F1 score for cuboid class is perfect, since I had said before that the gripping pattern is very distinct. The cylinder and sphere show the precision of 91% approximately, and sphere of 89%. Overall accuracy turns out to be about 92.85%. The resources, which are basically the video link of the demonstration, the implementation code, and the dataset and the module, have been made available in these links. I would like to thank IEEE Sensors for providing me this opportunity to present our work. Thank you.